Okay, so where were we last time? Remember, we wanted to declare new types, yeah, because at the moment what we have is that we know how to write new functions, but we don't know how to write new types. So this is what we are going to do today. Now there are multiple reasons why one would want to have new types. Okay, one is obviously when you can't do without them. For instance, if I want to define a linked list, then obviously I know that it's a node with which has some outgoing pointer. Or if I want to define a binary tree, then I need to have a node with two pointers in it and all this kind of things. But we don't have pointers in Haskell. But what we have is we have we can say that a binary tree is a node which contains one data element, and then it contains one left subtree and one right subtree. So it's a recursive definition. So if you want to define such new kind of things, then you need to have new types. But that is not the only reason why one would want to have types. There can be lesser reasons why one wouldn't want to have types. Can you give me some example? Hello? Abhishek? Yeah, can you give me some reason apart from defining new objects to have new types? To make the code cleaner, can you elaborate? Can you elaborate? How do you make code cleaner by having new types? Yeah, but that already comes under having new kinds. Yeah. So for instance, having a discipline of coding. For instance, imagine I am declaring a variable, but it takes a limited set of values. Yeah. For instance, imagine I have a value or variable which takes only even values, even numbers. Okay. Now there is no way in C we can say that this is an integer which takes only even values. We will have to declare it as an int, and everywhere we want to check whether that value, whenever we change the value, we will make sure that it's an even. That's one way of ensuring discipline. But that discipline is ensured by us, isn't it? Compiler doesn't help in that. Agree? But in Haskell, there is one way of getting around that in C. For instance, you say that if it is a finite set of values, you say that it's an enum type and it can take only these values. So then compiler will start checking whenever that variable is accessed, compiler will check that it is one of these enum values. That's one. So similarly, there are such kind of provisions in Haskell. Okay. Now let's look at what are the available provisions in Haskell. So one so So one thing to do, one way of defining new types in Haskell is just by saying that, okay, I'm going to define a new type, but this is nothing but an old type, but it's a new name for an old type. That is done by the keyword type. For instance, when you say type string equal to list char, this is exactly the definition of char, string. Okay, you're not defining a new type per se, you're just giving an alias. Yeah, you know that word, alias. It's an alias for a existing type. All right. Or instance, you can say position. You say position is nothing but a tuple of int and an int. Okay. Now remember that all functions starts with lowercase letter, all types starts with uppercase letters. All right. So now if I have defined a new type called position, now I can use that in my function definition. For instance, if I want to say move, if I want to define a function called move, and move takes, let's say, move north. Okay, now move north is a function which takes a position and gives back a position, and move north will be, move north of xy will be x comma y plus 1. Yeah, for instance, you have x and y, and then if you want to move north, you just, x remains the same, y increments y1. Similarly, you can have move south, which is xy will be x minus 1 y. Now x y minus 1. Move east will be x plus 1 y. Now move east will be x plus 1 y, and move west will be x comma xy will be x minus 1 y. Okay, so this is one way of defining, one way of using types. So move takes a type which is position, but position is nothing but in comma int. Okay, so this is nothing but you use an alias for existing types, and these kind of types are not primitive types. Not primitive types, but algebraic types. Primitive types, algebraic types, meaning that algebraic types meaning types synthesized from primitive types using Cartesian product. Unions, etc. Okay. For instance, in comma int, a tuple is nothing but a Cartesian product. Yeah. When you say n cross n, you write it as x comma y, and that is nothing but a Cartesian product of n and n. And if you want to say I don't know, we are not using sets at the moment, but if you have sets, it will be unions and so on. Okay. Now what is more important for us is, so this one is actually types as aliases of existing ones. Now I have other thing which is really new types. So this is where we define really new types. Are you there? Hello? All right. I mean, because you're not responding, that's why. You have to respond, all right? All right. Okay, so now we want to define really new types. For instance, if I want to define a binary tree, I can't write a binary tree like position, for instance, because I don't have a binary tree is really a new thing. Because a binary tree is a recursive definition. A binary tree node contains a value and two other binary trees. So I really need something new to define what is a binary tree data type. And this type mechanism is not enough. Okay, that is where data comes in, the keyword data. Okay, now data allows you to really define new types. Now what are you going to do in data? So the data's keyword will be usually like this. Data will be data type name equal to a grammar for generating the values in the type. Okay, this is how it will look like. It will be, you will say you will give a name for the type, and you will say a grammar for generating the values in the type. For instance, in Haskell, for instance, you will say data, and let's say unique. This is my type name, and there is exactly, imagine there is only one value. For instance, in the Haskell, then you will usually say unique equal to unique. Okay, now I can have a function return which is unique, which takes, let's imagine, which takes unique. No, let's not get into very complicated stuff. So for instance, this is one possible definition, because I am just saying that data and the type name will be unique. It has exactly one value, so therefore we can give it any name, but when your type has exactly one value, usually people give it that same name as the type name. So data unique equal to unique will be a valid valid type. So in which the name of the type is unique and the values are unique. Let's imagine data 2. Okay, so the type name is 2, and let me go and give it like first and second. Okay, so this type has the name 2, and it has two values in the type, which one is called first, one is called second. Now if I want to, let me write a function which uses this. Okay, for instance, we have a function called FST, which takes let's imagine it takes it takes 2 and a tuple a comma b, okay, and that's going to be complicated. Okay, so this function first, let's make it a comma b, and second will take 2 arrow a comma b to b, and I'm going to put a prime there just to make sure that and FST prime of first and a comma b will be, let's put it x comma y, will be x, and SND prime of second and x comma y will be y. Do you understand what I just wrote? Yes. Yeah. So instead of this first and second, let's put it select. Yeah. Function name should be what? Yeah. Yeah, if yeah, yeah, so in that case we'll have to write it as like this, select. But in that case we will not be able to write it as A and B. We'll have to use the same A. Yeah. And if I say first xy will be x, cell second xy will be y. Does it make sense now? Uh, no, because that is not allowed in Haskell. When you define a type of when you write A and B, and when it goes to A and it goes to, first of all you can't have two conflicting types. So if you write A goes to A comma B goes to B and A comma goes to A, there are two possibilities. Either the compiler will complain immediately saying that multiple definitions of that function, and even if it doesn't have a problem, it will unify A and B and say that A equal to B. Okay, but most likely it will complain at that stage itself, at the type definition stage itself. So it necessitates that you cannot have two different types. Now let's try to execute this. No, we don't need deriving show in this at the moment, because we are not displaying first or second. Yeah, we don't have to display. Pardon? Yeah, we can use it. Yeah. Yes. If this function was returning one of these first or second, um, then we wouldn't have needed it. Okay, now if I say select first 2 comma 3, it gives me 2 3, and if I say select second, it gives me 3. Yeah, so now what we have done is really we have defined a new type, and that type has exactly two values, first and second, and that we have written a function called select or cell, which will actually make a choice based on whether it is a first or second. So the here 2 is a new type name, and first or second is a grammar generating the values in this type. Yeah, you understand what is a grammar? A grammar is nothing but a sequence of rules, production rules. Yeah, so in this case the grammar is 2 equal to first or second. That's a grammar. It says that 2 either generates first or generates second. So this way, if you write a type, then you can only get finitely many values, because you will say type type 15, and then you might have 15 values here, but it is still finitely many values. So if you want to generate an arbitrary many elements, and which is true for the case of binary tree, because there are infinitely many binary trees of finite depth. Yeah, for every finite length you have a binary tree, finite depth you have a binary tree. So when you define a new type called a binary tree, there will be infinitely many values in it. So if you want to define an type which contains infinitely many elements, then you really need to use recursion in types. Okay, and so that is what we are going to do next. So let's try to define. Um, let's first to define the type called list, because list is something which we know. So now if I'm going to define list, I'll say data, and let me say this is my, I'm going to call it LL. LL stands for linked list. Okay. LL is, or I'm going to write a grammar for all the linked lists, or just linked list. I mean, instead of list, I'm going to say it linked list, because I'm going to use an analogy with the way you do things in C. So a linked list is either a null list, so it's either null, or what? Or it is a linked list, or it is let's put it this way, it is append, or let's call it extend LL int and LL. Okay. So a linked list is either null, or it is extend an integer with a linked list. So what are the this is a grammar, you have to see it as a grammar. What are the elements in this grammar? One is obviously null, none is an element. Another element is extend some integer value. Okay, int null, that's also an element. So when you put an int, when you really take it, this int will be some concrete value. It will be like x1, null will be a value. That's an element of this linked list. Another thing will be 2 extend 1 null, that's another value. Extend 1, extend 3, extend 4 null, that's another linked list, and so on. Yeah, any doubt? No, that we are declaring that. Can I just put it as int LL? That's what you're asking? We put in so that it is parsable, you know. So if you don't, if you just put int LL, so then what you will have is that int, and then at the end you will have a null. And in this case, it is not parsable because why it is, hello? So if I didn't have that extent, then what will happen is that it will look like this, null it will look like this, null, then 1 null, that's another thing, 2 3 null, that's another element, 2 4 5 null, these are all elements of this linked list. Yeah, but now there is a problem. Now unless we are careful, what is going to happen is that when you pass arguments, it may not be possible to parse this, but you should be able to it records what? It records space, but the point is that, and so the parsing is one problem. Okay, now the second problem is this, that you don't see types as just grammar. Okay, because so far I have introduced them as grammar, but actually what you're actually doing is that you need to have a constructor function. Everything will look like this, grammar for generating type. Let me put it here, data type constructor equal to value constructor arguments on value constructor etc. Okay. So that means that when I write null, it's a function. It's a function which takes 0 arguments. When I write something here, it has to be a constructor function which has not been defined yet. It has to be new. And here, but I can't leave it as int. So I have to give something. So that's why we have to put it as int. So for instance, I will say ex int with ll. Alright? Are you following? So here its construction functions are taking 0 values, 0 arguments. Here this construction takes 0 arguments. This construction function e takes 2 arguments, which is one is an int, one is a linked list, and returns me a linked list which is of this type ll. Yeah. So the values will be e null, e1 null, e2, e3 null. These are all valid elements of this grammar. Yeah. Okay. Valid elements of the above grammar. Okay, so now let's try to use this data, this newly defined type, to actually define to do some list operations. Okay, so I want to say head. Okay, so head defines the head of my linked list. Head takes an ll and returns me an int, because my linked list is over int. So what should be head of? So now what I'm going to do is that every element of this type looks like either of the form null or e then followed by some argument. So therefore I can use pattern matching. So I'm going to use pattern matching. If the head is null, then I'll say I don't actually write a case for that because I want it to be, let's say, an error. So for instance, if the head is e and then some x and some y, then I'll say it's x. Okay, clear? So now let's put some linked list. So some list L1 equal to E1, E2, E3, E4 and null. Okay. Import declaration of yeah. Thank you. Okay, so now let's try to do head of L1. Head of L1 is 1. Let's do tail. tail of LL. Can you give me the definition? EXY will go to tail of LL goes to, yeah, yeah, and tail of null, null, yeah, yeah, it's null. So then tail of L1 will be. So now we see that there is an error, and that error is because I am not displaying, I haven't told Haskell compiler how to declare, how to show this type. For instance, I want it to be, if I want it to be displayed like null, E1 null, E2, E3 null, then I'll tell Haskell compiler, don't bother, just display them like null, E1 null, E2 null, E2, E3 null, etc. That is where we write deriving show. Yeah, so now it says that, tail of L1 will be E2 of E3 or E4 of null. Now let's write something, let's write reverse of LL will be an LL. So how do we write reverse of LL? Shika? How do we write reverse of LL? Pardon? Okay, Shika does not seem to have. So I'm going to write reverse of null will be nothing but null. Yeah. And reverse of E X Y will be, how do we write? Abhishek? No, you have to make it in our stuff. So I have to first write E, yeah, reverse of Y and reverse of Y EX. So this one work, yeah? So how do we do reverse? So this is obviously wrong. Why is it wrong? Because when I look at E takes two things. One, the left argument E takes is an int, yeah, and the right argument is a linked list. But if I want to, when I want to do reverse, I want to find out the reverse of Y, which is a list, and then I want to find, and X is an int, but then I want E to be, X to be at the end of Y. So I need to define a new function, isn't it? So let's first write an append function. Let's write append of LL. It takes two lists, LL, and returns me a third list. Yeah. So now how does append work? Append of anything with null will be append of anything with null with anything is X. Yeah. And append of X with null is also X. and append of E x y and z will be what? E of append of E x append of y z. Yeah. Let's first see whether it is correct. So append of L1 non-exhaustive patterns in append. What is non-exhaustive pattern in append? What is wrong with this one? Let's figure it out. So I have two lists. I take two lists and I return a third list. So if the first list is null and the second list is x, then I return x. If the first list is x and the second list is null, then I return x. So actually I don't need this. I'm going to go with this. Okay. Because I'm going to recurse on the first argument. So if the first list is non-empty, it's of the form E, X, Y and Z, then what I do is that first I extract that X and I can create a new list with E, X, and then I append Z to Y. Okay, so this will return me a list, and I put that list, I put X at the beginning of that list. So that's why I get E, X, Y of append of X, Y, Z. That's fine. Now if I have append of null and let's say Z, then I should return Z. Yeah. So now let's see why this one has a problem. Non-exhaustive patterns in function append. Let's try to see. Let's try to debug. E1 null and E2 null. That's also error. E2 null, that's fine. So if I have E1 null and Z, do you see this error? There is a double P there. That's error. Okay. So now if I do this, it's correct. If I do this, that's also correct because I have 1, 2, 3, 4 followed by 1, 2, 3, 4. So now we have an append function. Are you following? All right. Yeah. So now let's do reverse with append. So how do we do reverse? Reverse takes a linked list and gives me back a linked list, and reverse of a null list is null list, and reverse of an E and XY will be, I have to first reverse Y and then I have to append X to the end of that list. That's all. So now X is not a list, that is true. Exactly. It should be E X null. Yeah, because that will be a list. So now reverse of L1 will be 4, 3, 2, 1. So now we know how to do reverse. Yeah. All right. So let me give you some exercises. Um, delete. So the function is delete del delete ll arrow int arrow ll arrow int. So what does it do? What does it do? Yeah, given linked list. Yeah. And what does count do? Exactly, in the list. What other list functions? Give me a complicated list function. Sort. Okay, folder. Very good. So folder, what does it do? It takes a function a arrow b and an ll. Okay, so now let's go back and see. Right now this list is hard coded to have only int, but there is a way in which we can make this linked list with arbitrary data. For instance, I say data lla, a new kind of linked list which is not fixed with int. I'll just say null or e, and I'll say a, and I'll say lla. Okay, so now what is this linked list do? In this linked list I have introduced a type variable. So this linked list can be of any type. So if I just say lla e let's remove this a, just do it. Okay, so if I just say minus, okay, now if I say e hello null, a will be taken to be string. So in this case the ll will be only strings, only list of strings. But if I say e5 null, it will be a list of strings for integers. I mean list of integers. So folder, what is the definition of folder? It takes a function which takes an a and a b and gives me back a b. Yeah, and I have a list of b. No, I have a this is what a folder is. Yeah, I have a function which takes an value a and a b and gives me back an a, and I have a value a and I have a list of b's, and at the end I'll have an a. Yeah, that's it. Hello. So you want to write it as b goes to a goes to a goes to b goes to b, and yeah, it's but it's just you just exchange a and b. So at the end also it will be b. Okay. So in this, okay, folder. All right, so write these three functions for this one. So now um, that is about list. Now how do we define a binary tree? When did we start? All, are you done? Are you tired? Yeah, so then let's stop for the moment and we will take it up sometime. I mean, so far, are you, I mean, you are comfortable doing this exercise? Delete, count, and folder. All right, so do that and we will get back tomorrow or day after. Yeah, all right. Thank you. Bye.